Physicists don't usually talk about defeat. They talk about challenges, puzzles, open questions. But there's a difference between a puzzle you haven't solved yet and a puzzle that seems to resist solution in a very particular way. One that keeps appearing, wearing different disguises, across entirely separate areas of physics. The strange thing isn't that we encounter difficult problems. It's that we keep encountering what appears to be the same difficult problem over and over, even as our theories become more sophisticated and our predictions more accurate. Start with something simple. Take 3 objects in space, 3 planets, 3 stars, doesn't matter, and try to predict their orbits using Newton's laws. 2 objects, solved completely in the 1600s. We have exact formulas. The math is elegant, closed, final. 3 objects, no general closed form solution is known. Not because we haven't found it yet, because the system becomes chaotic. The equations are perfect. Newton's laws work flawlessly. But extract a closed form answer that tells you where these 3 bodies will be at any future time. No such general solution exists, not because it won't be done, but because no general solution is known. That was Newton's first real worry, actually. And here's what makes it unsettling. We're not talking about some exotic corner of physics. This is classical mechanics, the foundation, the part that works. And yet even here, with 3 bodies obeying perfectly well understood laws, the mathematics produces behaviour that is highly sensitive to initial conditions in detail. We can simulate it, we can approximate it, but we cannot solve it in the way we solve 2 bodies. The problem isn't insufficient computing power or missing information. The problem is that the system itself resists the kind of mathematical closure we expect from a deterministic laws. You might think this is just an isolated quirk of orbital mechanics. It's not. The same pattern appears in fluid dynamics. The Navier-Stokes equations describe how fluids flow. Water, air, blood, anything that moves like a continuous substance. These equations were written down in the 19th century. They work. Engineers use them to design aircraft, to model weather, to understand blood flow. The predictions match reality with extraordinary precision when you run computer simulations. But here's the problem. It remains unknown whether smooth solutions to these equations always exist in 3 dimensions. It remains unknown whether the mathematics can develop singular behaviour, producing infinities, discontinuities, or mathematical objects that stop making physical sense. This isn't a minor technical detail. The Clay Mathematics Institute listed it as one of 7 Millennium Prize problems. Solve it and you get $1 million. But more importantly, you'd understand something fundamental about how complexity emerges from simple rules. Because the Navier-Stokes equations aren't complicated in their structure. They're elegant, compact, based on straightforward physical principles. And yet they contain within them the seeds of turbulence, one of the last major unsolved problems in classical physics. We can see turbulence, we can measure it, we can simulate it on computers, but we cannot derive from first principles a complete theoretical explanation of why it behaves the way it does. The equations seem to know something we don't. Notice the pattern? In both cases, the 3-body problem and turbulence, we have equations that work. The predictions match observations. The mathematics is not wrong. But something about the system prevents us from extracting the kind of complete understanding we expect. It's as if the equations themselves contain a locked room we can peer into, but never quite enter. Now move to quantum mechanics. Here the situation becomes more philosophically uncomfortable. The Schrödinger equation tells you how quantum systems evolve over time. It's deterministic, precise, mathematically beautiful. But when you actually measure a quantum system, when you look at it, something different happens. The system collapses from being in multiple states simultaneously to being in one definite state. The equation doesn't describe this collapse. There's a second rule, the measurement postulate, that you have to add by hand. And these two rules, the smooth evolution described by Schrödinger and the sudden collapse during measurement, appear difficult to reconcile. This has been controversial for over 80 years. It's called the measurement problem. Not because we can't make measurements, we can with extraordinary precision, but because the theory gives us no clear account of what a measurement actually is or when it happens. You might think, well, a measurement happens when we observe the system, but observation isn't a physical concept. It's not in the equations. Does observation require consciousness? Does it happen when a photon hits a detector? When the detector sends a signal to a computer? When a human looks at the computer screen? The mathematics is silent on this. The theory works. Quantum mechanics is the most precisely tested theory in the history of science. But it doesn't tell us what's actually happening when we measure something. Different physicists have proposed different answers. Some say the wave function doesn't really collapse. The universe splits into multiple branches. Some say consciousness causes collapse. Some say the whole question is meaningless, that quantum mechanics only predicts measurement outcomes, not what happens between measurements. There is no consensus, not because the evidence is unclear, but because the mathematics itself seems to resist giving a clear physical picture. The equations are precise. The interpretation remains ambiguous. Here's where things get quietly uncomfortable. You might notice that in all three cases, orbital mechanics, fluid dynamics, quantum measurement, the problem isn't that our theories are wrong. They work. They make predictions that match reality. The problem is that the mathematics seems to contain something we cannot fully extract or interpret. In the three-body problem, we cannot extract a closed-form solution. In turbulence, we cannot extract a complete theoretical understanding. In quantum mechanics, we cannot extract a consistent physical interpretation. This is not how we usually think about physics. We think, if the equations are right, we should be able to solve them, understand them, interpret them. But what if that's not how it works? What if some physical systems, even when governed by perfect equations, inherently resist complete mathematical closure? Move to general relativity. Einstein's equations describe gravity as the curvature of space-time. They work spectacularly well. They predicted the bending of light around the sun, the existence of black holes, gravitational waves, all confirmed. But the equations also predict singularities, points where the mathematics breaks down completely, where space-time curvature becomes infinite, where the equations themselves stop giving meaningful answers. The most famous example is at the center of a black hole. General relativity tells us that matter collapsing under its own gravity will continue collapsing until all of it reaches a single point of formally infinite density, a singularity. But here's the thing. Physicists don't think singularities are real physical objects. They think singularities are the theory telling us it has reached its limit. The mathematics is breaking down. The theory needs to be replaced with something else, presumably quantum gravity, which we don't have. But notice what's happening. General relativity is not wrong. It correctly predicts everything we can actually observe about black holes. The event horizon, the gravitational waves from mergers, the orbits of stars around supermassive black holes. The theory works, but when you push it to its logical conclusion, it produces mathematical objects, singularities that don't make physical sense. The theory succeeds and fails simultaneously. Same thing happens when you try to combine quantum mechanics and general relativity. Both theories work perfectly in their own domains. Quantum mechanics describes the very small. General relativity describes the very large. But when you try to apply both to the same situation, say the interior of a black hole or the first moments of the Big Bang, the mathematics explodes. You get infinities, not just one infinity, but infinities upon infinities. The equations become meaningless. Physicists tried to fix this with a technique called renormalization. It's a mathematical procedure that essentially absorbs infinities into other quantities, leaving you with finite, measurable predictions. It works. Quantum electrodynamics, built on renormalization, is the most accurate theory in physics. Predictions match measurements to 10 decimal places. But even the physicists who developed renormalization were uncomfortable with it. Richard Feynman called it a dippy process. Paul Dirac said it was not sensible mathematics. They were essentially subtracting infinity from infinity to get finite answers, a procedure that violates basic mathematical rules. And yet it works. The predictions are correct. The theory is not wrong. But something about the mathematical structure feels improvised, like we're applying a patch to cover something we don't understand. The theory succeeds in making predictions while simultaneously suggesting that something fundamental is missing from our understanding. You're probably noticing the pattern by now. Across completely different areas of physics, classical mechanics, fluid dynamics, quantum mechanics, relativity, quantum field theory, we keep hitting the same conceptual wall. The equations work. The predictions match observations. But when we try to push deeper, to extract complete solutions, to understand the full physical meaning, to combine theories, the mathematics resists us. It produces chaos, infinities, ambiguities, or simply refuses to give closed-form answers. This is not a problem of insufficient intelligence or inadequate tools. Some of the greatest minds in history have worked on these problems. We have supercomputers that can simulate systems with billions of variables, and still the same pattern emerges. The mathematics that describes reality seems to contain a barrier we cannot cross. What makes this particularly strange is that physics has always proceeded by finding deeper explanations. Newton unified terrestrial and celestial mechanics. Maxwell unified electricity and magnetism. Einstein unified space and time. Each unification revealed simpler, more fundamental laws beneath the apparent complexity. We expect this pattern to continue. We expect that if we dig deep enough, we'll find the final theory, the complete mathematical description of reality. But what if that expectation is wrong? What if the universe is structured in such a way that complete mathematical closure is impossible? Not because we haven't found the right theory yet, but because the universe itself resists being fully captured by mathematics. This is where the question becomes less about physics and more about the relationship between mathematics and reality. We tend to assume they match perfectly, that the universe is, at bottom, mathematical, that if we find the right equations, we'll have a complete description of everything. But our actual experience with physics suggests something more complicated. The equations work. They make accurate predictions, but they seem to contain locked rooms, barriers we cannot cross, questions they cannot answer, even when applied perfectly. Perhaps the strangest thing about these mathematical barriers isn't that they exist. It's that they're invisible until you look directly at them. You can use quantum mechanics for decades, calculating the behavior of atoms and particles with extraordinary precision without ever encountering the measurement problem. You can simulate fluid dynamics, design aircraft, model ocean currents, all while the fundamental nature of turbulence remains completely unexplained. The equations work. The predictions match observations. The barrier only appears when you ask a different kind of question. Not what will happen, but what does this mean? This is where physics begins to feel less like a map of reality and more like a user interface, a system that gives you the right outputs without necessarily revealing what's happening underneath. Consider what happens when you try to move between these successful theories. Quantum mechanics describes the microscopic world with incredible accuracy. General relativity describes the large-scale structure of space-time equally well. But when you try to apply both simultaneously to describe what happens at the center of a black hole, or during the first moments of the Big Bang, you don't get a more complete picture. You get mathematical nonsense. The equations produce infinities, not just large numbers, but literal infinities that make calculation impossible. Physicists try to address this with string theory, a framework that attempts to unify quantum mechanics and gravity by replacing point particles with tiny vibrating strings. The mathematics is elegant. The theory contains gravity naturally. But after 40 years of development, string theory has produced no uniquely confirmed experimental predictions. It requires extra dimensions we cannot observe. It predicts a vast landscape of possible universes with no way to determine which one we inhabit. The theory is mathematically consistent but empirically invisible. Loop quantum gravity takes a different approach, attempting to quantize space-time itself. It avoids some of the problems of string theory, but encounters its own barriers. The equations become so complex that they resist exact solutions. Approximation methods work only in limited cases, and like string theory, it has yet to make contact with experiment. Both theories might be correct, both might be wrong, or the question itself might be malformed, like asking what happens north of the North Pole. Freeman Dyson suggested something along these lines, that the quantum and classical realms might be fundamentally separate, unable to be unified because they describe different aspects of reality that don't overlap at any scale we can access. If he's right, then the search for a theory of everything isn't just difficult, it's pursuing something that doesn't exist. This raises an uncomfortable possibility. What if physics keeps encountering the same barrier, not because we haven't been clever enough, but because the universe itself contains a boundary? Not a physical boundary in space, but a conceptual boundary in our ability to extract complete mathematical descriptions of how reality works. Think about what physics actually does. It identifies patterns, expresses them mathematically, and uses those expressions to make predictions. This process has been spectacularly successful. But success in prediction doesn't necessarily imply success in explanation. You can have a theory that tells you exactly what will happen without telling you why it happens or what it means for that thing to happen. The spectral gap problem makes this distinction explicit. In quantum mechanics, the spectral gap determines whether a material can be a superconductor or whether it will exhibit certain magnetic properties. It's a yes or no question. Does this quantum system have a spectral gap or not? The question is perfectly well defined. The mathematics is rigorous. And in 2015, mathematicians proved that the question is undecidable. Not just difficult, undecidable in the same sense that the halting problem in computer science is undecidable. There exists no algorithm, no matter how sophisticated, that can determine whether an arbitrary quantum system has a spectral gap. This was the first major problem in physics proven to be undecidable in a rigorous mathematical sense. Not unsolved, unsolvable. The proof spans 146 pages and establishes that certain questions about quantum systems are mathematically equivalent to questions that Alan Turing proved cannot have algorithmic solutions. The implications are profound. It means that even with a perfect, complete description of a material's microscopic properties, every atom, every interaction, every quantum state, you cannot necessarily predict its macroscopic behavior. The information is there. The question is well defined, but the answer is mathematically inaccessible. This isn't about computational limits or insufficient data. It's about the structure of mathematics itself. Some true statements cannot be proven, some well-defined questions cannot be answered, and physics has now encountered such questions in its fundamental theories. You're probably starting to sense that these aren't isolated problems. They're symptoms of something deeper, a consistent pattern across apparently unrelated areas of physics. When you try to extract complete solutions from a deterministic equations, you encounter chaos. When you try to understand turbulence from first principles, the mathematics becomes intractable. When you try to unify successful theories, you generate infinities. When you try to interpret quantum mechanics, you encounter the measurement problem. When you try to determine basic properties of quantum systems, you hit undecidable questions. Each time the failure has the same structure. The mathematics is correct, the predictions work, but complete understanding remains just beyond reach. It's as if reality allows us to calculate, but not to comprehend, to predict, but not to fully explain. And here's what makes this particularly unsettling. These aren't fringe theories or speculative ideas. These are the most successful, most rigorously tested theories in the history of science. Quantum mechanics has been verified to extraordinary precision. General relativity has passed every experimental test. The three-body problem uses nothing more exotic than Newton's laws. The Navier-Stokes equations have been known for nearly 2 centuries. These are the foundations of modern physics, and they all contain the same type of barrier. What this suggests is that the barrier isn't in the theories themselves. It's in the relationship between mathematics and physical reality. We've been assuming they match perfectly, that the universe is fundamentally mathematical in a way that makes complete description possible. But our actual experience suggests something more complicated. The universe is mathematical enough to allow precise prediction, but not mathematical enough to allow complete explanation. The equations work, but they resist revealing their full meaning. This creates a peculiar kind of knowledge. We know how to calculate what will happen. We know how to build technology based on these calculations. But we don't fully understand what these calculations represent. It's functional knowledge without complete comprehension, like knowing how to use a tool without understanding what the tool is made of or why it works. Singularities illustrate this perfectly. They appear throughout physics, in general relativity when matter collapses, in solutions to wave equations, even in the simple case of a billiard ball bouncing off a perfectly rigid wall. Mathematically, a singularity is a point where equations produce infinity. Physically, we're fairly certain that infinities don't actually occur. The singularity is a signal that our mathematical description has broken down, that we're applying equations beyond their domain of validity. But here's the strange part. Singularities often point the way to new physics. The ultraviolet catastrophe, infinite energy predicted for black body radiation, led to quantum mechanics. Infinities in quantum field theory led to renormalization, and eventually to our understanding of how forces work at different energy scales. Singularities are simultaneously problems and hints. They mark the boundaries of our current understanding while suggesting where to look next. Roger Penrose proposed the cosmic censorship hypothesis to deal with singularities in general relativity. It states that singularities must always be hidden behind event horizons, that nature conspires to prevent naked singularities from appearing where we could observe them. The hypothesis has never been proven. Counterexamples have been found in special cases, but it persists as a conjecture because it captures something physicists intuit about the structure of reality, that breakdowns in our mathematical descriptions are somehow quarantined, kept from affecting the rest of the universe. Whether that's actually true remains unknown. The hypothesis might be correct, it might be wrong, or it might be asking the wrong question, treating mathematical artifacts as if they were physical entities that need to be hidden, rather than recognizing them as signals that our framework needs revision. What makes this pattern particularly difficult to dismiss is how it appears independently across problems that seem unrelated. The three-body problem emerges from classical mechanics. Newton's laws applied to gravitational attraction. Turbulence arises from fluid dynamics and the Navier-Stokes equations. Renormalization appears in quantum field theory when calculating interactions between particles. Singularities show up in general relativity when mass becomes sufficiently concentrated. Each problem originates in a different domain, uses different mathematics, describes different phenomena, yet they share a common structure. Equations that work perfectly for making predictions but resist yielding complete understanding. Consider the three-body problem. It's deceptively simple to state. Take three masses, say 3 stars or planets, moving under their mutual gravitational attraction. Given their initial positions and velocities, predict where they'll be at any future time. For two bodies, this problem was solved centuries ago. The orbits are ellipses, circles, parabolas, or hyperbolas, conic sections described by elegant equations that let you calculate positions for any time you choose. Add a third body and everything changes. The problem becomes what mathematicians call non-integrable. There's no general formula, no closed-form solution. You can simulate the motion numerically, advancing the system forward in tiny time steps, but you can't write down an equation that directly gives you the answer. Even stranger, the motion itself becomes chaotic for most initial conditions. Tiny differences in starting positions lead to completely different trajectories. The system becomes effectively unpredictable in practice, not because we lack information, but because prediction requires infinite precision in the initial state. This was Isaac Newton's first real worry. He could predict planetary motion with extraordinary accuracy when considering only the Sun and one planet. But Jupiter's influence on Saturn, Saturn's influence on Jupiter, these mutual perturbations introduced complications that his methods couldn't fully resolve. He suspected the problem ran deeper than mere computational difficulty. 300 years of work by some of the finest mathematical minds have confirmed his intuition. We have explicit solutions for exactly 5 families of orbits, 3 discovered by Leonhard Euler in 1767, 2 more by Joseph Louis Lagrange 5 years later. That's all. 5 special cases out of infinite possibilities. Henri Poincaré proved in 1890 that this scarcity isn't accidental. The three-body problem contains deterministic chaos. Not randomness, the motion is completely deterministic, but sensitivity to initial conditions so extreme that long-term prediction becomes effectively impossible in practice. What appeared to be a straightforward extension of solved mechanics revealed something unexpected about deterministic systems. They can be practically unpredictable, even when governed by laws we understand completely. Now shift to fluid dynamics. The Navier-Stokes equations describe how fluids flow. They account for pressure, viscosity, momentum conservation. Written down in the 19th century, these equations have been applied successfully to countless engineering problems. Aircraft design, weather prediction, blood flow modelling all rely on solutions to these equations. Yet we still cannot prove that smooth solutions always exist in 3 dimensions. The Clay Mathematics Institute considers this important enough to offer $1 million for either a proof that smooth solutions always exist or a demonstration that they sometimes break down. After more than 20 years, no one has claimed the prize. The equations work, engineers use them daily, but their mathematical properties remain mysterious. Do they always produce sensible answers, or can they sometimes generate infinities or discontinuities that make physical interpretation problematic? Turbulence embodies this mystery. When fluid flows slowly past an obstacle, the motion is smooth and predictable. Increase the speed and the flow becomes turbulent, chaotic swirls and eddies that seem almost random. The transition happens abruptly. The equations governing both regimes are identical. Nothing in the mathematics explicitly distinguishes smooth flow from turbulent flow. Yet the behaviours are radically different. Turbulence has been called one of the last unsolved problems of classical physics, and the label fits. We can simulate it, measure it, even use it practically. But we lack a fundamental theory explaining why it behaves as it does. The Navier-Stokes equations form what's essentially one enormously complicated nonlinear oscillator. Under some conditions, solutions remain stable. Under others, they become unstable in ways that generate the spatial and temporal chaos we recognize as turbulence. The equations contain all the physics needed to describe this behavior, but extracting understanding from them has proven extraordinarily difficult. They represent a highly nonlinear system with many degrees of freedom, whose solutions exhibit patterns we can observe, but not fully explain. This brings us to renormalization, which appears in a completely different context but follows a similar pattern. In quantum field theory, calculating the probability of particle interactions involves summing contributions from all possible intermediate processes. An electron can emit and reabsorb a virtual photon. That photon can briefly split into an electron-positron pair. Those particles can emit more photons. The possibilities multiply without limit. When physicists first attempted these calculations in the 1940s, they encountered infinities. The mathematics produced divergent results, infinite probabilities, infinite energies. The theory seemed to lose predictive meaning precisely where it should have worked best. Then came renormalization, a procedure for absorbing these infinities into the measured properties of particles. The electron's observed charge and mass already include the effects of virtual particles. By carefully redefining terms, physicists could extract finite predictions that matched experiments with extraordinary precision. But renormalization troubled many of its developers. Richard Feynman called it a dippy process and said having to resort to such mathematical sleight of hand prevented proving that quantum electrodynamics was self-consistent. Paul Dirac, who pioneered the technique, later wrote that it was just not sensible mathematics. The objection wasn't that renormalization failed, it worked spectacularly. The concern was that it seemed to involve manipulating divergent quantities to obtain finite answers, a procedure that sits uneasily with standard mathematical rules. The physical interpretation remains debated. One view suggests the electron has an effectively unbounded bare charge at its core, but quantum field effects, virtual particles appearing and disappearing, screen this charge, so experimentalists measure only a finite effective value. Another perspective treats the infinities as artifacts of pushing the theory beyond its valid domain, signals that new physics must appear at higher energies. Either way, renormalization represents a controlled way of dealing with mathematical breakdowns that arise when we push our theories to their limits. These problems share more than a superficial similarity. They all involve non-linearity, situations where effects don't simply add up in proportion to causes. They all generate behavior that's difficult, or in some cases impossible to predict from first principles despite being governed by well-understood equations. They all suggest that complete mathematical description may be unattainable, even when prediction remains possible within certain limits. Consider what this implies about the relationship between mathematics and physics. For centuries, the success of mathematical physics encouraged a particular view that the universe is fundamentally mathematical, that its behavior can be captured in equations that we can solve to extract any information we need. The three-body problem challenged this view by showing that solvable doesn't always mean integrable. Turbulence reinforced the lesson by demonstrating that having the correct equations doesn't guarantee understanding the solutions. Renormalization added another layer by showing that even our most successful theories might contain procedures whose mathematical justification remains uncertain. What emerges is a picture of physics as a discipline that has learned to work around fundamental limitations. We develop numerical methods for three-body systems. We create computational models of turbulent flows. We apply renormalization techniques that yield accurate predictions. As these approaches work, they let us build technology, make forecasts, design experiments. But they're workarounds rather than solutions in the traditional sense. This distinction matters because it affects how we think about scientific progress. If every problem is potentially solvable, given enough time and insight, then current difficulties are temporary obstacles. But if certain problems are inherently resistant to complete solution, if the mathematics itself contains barriers we can't overcome, then we need different expectations about what understanding means. The question isn't whether physics will continue advancing. It will. The question is whether that advancement will take the form of increasingly complete explanations or increasingly sophisticated methods for working with persistent mysteries. The evidence from these recurring problems suggests the latter. We're learning to calculate more precisely, simulate more accurately, predict more reliably. But we're not necessarily getting closer to the kind of complete theoretical understanding that earlier physicists might have expected. The spectral gap problem takes this pattern to its logical extreme. Here, physics doesn't just encounter a problem it can't solve, it encounters a problem it can prove it can never solve. The spectral gap describes the energy difference between a quantum system's ground state and its first excited state. Understanding whether a material has a spectral gap determines whether it conducts electricity, whether it's magnetic, whether it undergoes phase transitions. Practical questions with real-world implications. In 2015, mathematicians proved something remarkable. They showed that determining whether a spectral gap exists in certain quantum systems is equivalent to the halting problem, a question Alan Turing proved no algorithm can answer. Not that we haven't found the right algorithm yet, that no algorithm can exist even in principle. The problem is undecidable in the formal mathematical sense. This represents a different kind of barrier than what turbulence or the three-body problem present. Those suggest practical limits on what we can calculate. The spectral gap problem reveals something deeper, that even perfect knowledge of a system's microscopic properties might not be sufficient to predict its macroscopic behavior. The derivation from small to large scales, the very foundation of reductionist physics, contains steps that cannot always be completed. What's particularly striking is how this limitation appears precisely where physics needs it most. The spectral gap determines phase transitions. It separates conductors from insulators, magnets from non-magnetic materials. These are the questions that underpin materials science, quantum computing, condensed matter physics. And for certain systems, the answer is provably inaccessible to any general algorithmic method. The proof doesn't mean we can't study specific materials. It means there's no general method, no systematic approach that would work for all cases. We can solve individual problems through approximation and simulation. We can build devices that work, but we cannot have the kind of complete theoretical framework that would let us predict behaviour from first principles in all circumstances. This matters because it suggests fundamental incompleteness isn't just a feature of our current theories. It might be intrinsic to how physics works. The universe might contain questions that are well posed, meaningful, and yet impossible to answer through any systematic procedure. Singularities provide another window into this same territory. When Einstein's equations predict that matter collapsing under its own gravity will reach infinite density at a single point, they're not describing something physical, they're announcing their own breakdown. The mathematics produces a result, infinite curvature, infinite density, that signals the theory has exceeded its domain of validity. Black holes contain singularities at their centres. The Big Bang appears to emerge from one. These aren't obscure edge cases. They're central to cosmology and astrophysics. Yet at these points, general relativity simply stops working. The equations generate infinities, and infinities in physics are generally signs that you've asked a question the theory can't answer. Roger Penrose proposed the cosmic censorship hypothesis to contain this problem. It suggests that singularities always hide behind event horizons, protecting the rest of spacetime from their consequences. If true, it would mean the universe conveniently shields us from seeing where its own description breaks down. But proving cosmic censorship has proven extraordinarily difficult. The hypothesis itself becomes another deeply unresolved problem, a proposed solution whose validity remains uncertain. What's revealing is how physicists respond to singularities. They don't typically treat them as real features of the universe. They treat them as markers indicating where new physics must appear. A singularity is a sign that your theory has reached its limit, that something you haven't accounted for becomes important. This is methodologically sound. But it also means accepting that our best theories come with built-in warnings. Beyond this point, I cannot help you. The pattern across these problems starts to become clear. Three-body systems show that deterministic laws don't guarantee predictable outcomes. Turbulence demonstrates that correct equations don't ensure theoretical understanding. Renormalization reveals that even spectacularly successful theories might rest on questionable mathematical foundations. The spectral gap proves that some well-posed questions have no algorithmic solution. Singularities mark the boundaries where our descriptions simply terminate. These aren't failures of physics in any conventional sense. The theories work. They make predictions that experiments confirm. Engineers use them to build technology that functions reliably. The problem isn't practical, but conceptual. We can calculate without fully understanding. We can predict without complete explanation. This suggests a particular view of what scientific theories are. Perhaps they're not descriptions of reality itself, but tools calibrated for specific scales and domains. They work within their applicable range, not because they've captured some eternal truth, but because they're well-tuned instruments for those conditions. Push them too far, to very small scales, very high energies, very complex systems, and they reveal their limitations. The quest for a theory of everything has run into exactly these issues. Unifying quantum mechanics and general relativity means combining theories that are individually successful but mutually incompatible. Quantum field theory treats space-time as a fixed background. General relativity treats space-time as a dynamic entity. Both work in their respective domains. Neither can be straightforwardly extended to cover the other's territory. String theory and loop quantum gravity represent different attempts to resolve this. Both approaches face the same basic challenge: making predictions that can be tested. String theory requires extra dimensions we can't observe directly. Loop quantum gravity quantizes space-time itself, but struggles to reproduce general relativity at large scales. Neither has produced the kind of distinctive, experimental signature that would confirm or refute its claims. Freeman Dyson suggested something provocative. Perhaps the incompatibility between quantum mechanics and gravity isn't a problem to be solved, but a feature to be accepted. If theories of quantum gravity are fundamentally untestable, if they make no predictions distinguishable from what we already observe, then maybe the classical and quantum descriptions can coexist without unification. Different frameworks for different domains, permanently. This contradicts the usual assumption that physics is moving toward a single, unified description. It suggests instead that we might be approaching a limit where further unification becomes meaningless, not because we lack the mathematical tools, but because the universe itself doesn't operate according to a single unified principle. The implications extend beyond these specific problems. If physics repeatedly encounters the same kind of barrier, situations where mathematics breaks down, where prediction becomes impossible, where theories reach their limits, then perhaps this pattern reveals something structural about the relationship between our descriptions and what they describe. One possibility is that we're hitting the boundaries of what mathematics can capture about physical systems. Mathematics excels at describing regular, law-like behaviour. It struggles with true complexity, with emergent phenomena, with situations where everything matters and nothing can be ignored. The three-body problem showed this centuries ago. We've been refining our methods since, but the basic limitation persists. Another view holds that these problems reveal the incompleteness of reductionism. Knowing the fundamental laws doesn't automatically tell you what complex systems will do. The derivation from microscopic to macroscopic contains steps that cannot always be completed, either practically or in principle. The universe is quantum at the smallest scales, but that doesn't mean we can derive chemistry from particle physics, biology from chemistry, psychology from biology. A third perspective suggests that the problems arise from treating our mathematical models too seriously, from confusing the map with the territory. Singularities, infinities, undecidable questions. These might be features of our descriptions rather than the universe itself. The real world might be perfectly well behaved, while our attempts to capture it in equations necessarily introduce artifacts and limitations. What's uncomfortable is that we can't definitively choose among these interpretations. Each has some explanatory power. None can be conclusively ruled out. And the persistent recurrence of similar problems across different areas of physics suggests that whatever is happening runs deeper than any particular theory or domain. This brings us to a question that's rarely asked directly. What if complete understanding simply isn't possible? Not because we're not smart enough or haven't worked hard enough, but because the nature of a physical reality doesn't permit the kind of exhaustive mathematical description we're seeking. What if the universe contains genuinely irreducible complexity, situations where no amount of calculation can replace actual observation, where prediction requires simulation rather than solution? This leads to something more uncomfortable than simple ignorance. If the universe contains aspects that cannot be captured mathematically, we face a choice between accepting perpetual mystery in specific domains or reconsidering what understanding actually means in physics. Neither option is satisfying. The first abandons the core project of theoretical physics. The second suggests that centuries of progress might have been building towards something fundamentally different from what we imagined. Consider what happens when we try to work around these limitations. Computational physics has become increasingly important precisely because analytical solutions often don't exist. Rather than solving equations to get formulas, we run simulations to see what happens. This works remarkably well for many practical purposes: weather prediction, turbulence modelling, materials science, all rely heavily on computation rather than closed-form solutions. But computation introduces its own limitations. Simulations require discretization, turning continuous space and time into grids of points. They require approximations, ignoring small effects to make calculations tractable. They trade exact prediction for approximate behaviour over finite timescales. And fundamentally, they answer what happens without explaining why it must happen this way. The understanding feels qualitatively different from what mathematical proof provides. Some physicists argue this distinction matters less than we think. If we can predict everything we can measure, if simulations match experiments, what more could understanding mean? This pragmatic view suggests that our attachment to analytical solutions reflects aesthetic preference rather than scientific necessity. Physics is about predicting observations, not satisfying philosophical intuitions about how nature should work. Yet the recurring nature of these impossible problems suggests they point towards something structural. They're not random gaps in our knowledge that will eventually be filled. They appear in systems governed by well-understood fundamental laws. The three-body problem doesn't indicate missing physics. Newton's laws are fine. The Navier-Stokes smoothness problem doesn't suggest fluid mechanics is wrong. The equations accurately describe fluid behaviour. These problems emerge from the mathematical structure of the theories themselves. This pattern appears most starkly in the spectral gap problem. Here we have a question about quantum materials where a perfect microscopic description, knowing every particle, every interaction, every quantum state, provably cannot determine certain macroscopic properties. The inability isn't practical, it's logical, in the same sense that Turing showed certain computational problems cannot be solved by any algorithm, no matter how clever or powerful. The implications extend beyond materials science. If deriving macroscopic behavior from microscopic laws is sometimes impossible even in principle, then the reductionist program has fundamental limits. Not every question about complex systems can be answered by studying their components, no matter how completely we understand those components. Some properties emerge from the whole in ways that cannot be predicted from the parts. This creates a peculiar situation. We have theories, quantum mechanics, statistical mechanics, general relativity that are extraordinarily successful within their domains. They make precise predictions confirmed by countless experiments. Yet when we try to use them to understand certain phenomena, we encounter barriers that appear to be logical rather than merely technical. The theories don't fail. They remain consistent and predictive, but they stop providing the kind of complete explanation we're seeking. Renormalization exemplifies this tension differently. Quantum field theory predicts infinities when calculating certain quantities. Rather than treating this as a fatal flaw, physicists developed renormalization, a procedure for extracting finite predictions by carefully subtracting infinities in a controlled way. This works spectacularly well. Quantum electrodynamics makes predictions matching experiments to extraordinary precision, but the procedure bothered many of its creators. Subtracting infinity from infinity violates basic mathematical principles. The resulting theory seems to depend on treating divergent integrals as if they were meaningful, then manipulating them in ways that don't strictly make sense. Feynman called it dippy. Dirac wrote that it wasn't sensible mathematics, yet it produces the most accurate predictions in all of science. Attempts to understand what renormalization means physically led to new insights about how physics changes with scale, about effective field theories, about why we can make predictions despite not knowing the ultimate theory at all energies. But these insights don't entirely resolve the original mathematical objection. The calculations still involve steps that aren't rigorously justified. The theory works, but its internal consistency remains questionable. This suggests that our most successful theories might contain elements that are pragmatic tools rather than fundamental truths. Renormalization might be a calculational device that gives correct answers without accurately representing the underlying structure of reality. If so, then even our best-tested theories are in some sense phenomenological. They describe what we measure without fully capturing what's actually happening. The measurement problem in quantum mechanics pushes this further. The theory contains two different rules for how quantum states evolve. When we're not looking, the Schrödinger equation describes smooth, deterministic evolution. When we measure, the state suddenly collapses into one definite outcome. These rules are widely regarded as difficult to reconcile. You can't derive measurement from the Schrödinger equation. You have to add collapse as a separate postulate. Decades of work have produced various interpretations attempting to resolve this. Many worlds eliminates collapse by saying all outcomes occur in different branches. Pilot wave theories add hidden variables determining outcomes. Spontaneous collapse models modify the Schrödinger equation. Each interpretation solves the measurement problem in a different way, but none has achieved consensus, and experiments haven't definitively ruled any out. What's revealing is that quantum mechanics works perfectly well for making predictions regardless of which interpretation you prefer. The different interpretations agree on all observable consequences. They differ only in what they claim is really happening between measurements. This means the empirical success of quantum mechanics doesn't tell us which interpretation is correct. The theory predicts observations, but underdetermines explanation. You might think future experiments will eventually distinguish between interpretations, but some of these interpretations are explicitly designed to be empirically equivalent. They make identical predictions in all possible experiments. The choice between them becomes philosophical rather than empirically decidable, a question about what we believe exists rather than what we can measure. This brings us back to the question of what physics can ultimately achieve. If our most successful theory admits multiple incompatible interpretations that are all consistent with every possible observation, then empirical adequacy doesn't guarantee understanding in any unique sense. We have mathematical machinery that predicts measurements, but that machinery doesn't determine a single story about what's happening. Singularities represent yet another manifestation of the same pattern. When matter collapses beyond a certain point, general relativity predicts that space-time curvature becomes infinite at a single point. Infinite density, infinite curvature, infinite tidal forces. The equations produce infinities, which means they're being applied beyond their domain of validity. They're telling us they can no longer describe what's happening. Many physicists suspect that quantum effects prevent true singularities from forming, but we can't calculate what actually happens because we don't have a theory of quantum gravity. General relativity fails at the singularity. Quantum mechanics fails when gravity becomes strong. We're left with a gap where neither theory applies and we have no replacement. The cosmic censorship hypothesis attempts to contain this problem by proposing that singularities always hide behind event horizons. If true, this means we can never observe the breakdown of our theories directly. The universe conspires to keep its failures hidden. This would be reassuring if we could prove it, but the hypothesis has resisted rigorous proof for decades. It might not even be true. So-called naked singularities might be possible. What's telling is how physics responds to these recurring impossibilities. Rather than treating them as crises demanding immediate revolution, the field often develops workarounds and continues making progress. Renormalization became standard practice despite its unsettled conceptual foundations. Quantum mechanics makes predictions regardless of interpretation disputes. Singularities are studied using various approximations and limiting cases. This pragmatic approach has been remarkably successful. Physics continues advancing, making new predictions, discovering new phenomena, but the accumulation of persistent, unresolved problems in different areas suggests that something systematic is being avoided rather than resolved. Each workaround succeeds within its domain, while leaving the underlying conceptual issues untouched. The question becomes whether these issues can ever be resolved, or whether they represent permanent features of how physics relates to reality. Perhaps complete mathematical description of all phenomena is simply impossible. Perhaps certain questions that seem physical are actually undecidable. Perhaps our theories will always contain elements that work pragmatically without being fully justified. This would represent a fundamental shift in how we think about physical law. The laws we use aren't arbitrary guesses. They're tested against reality constantly, and they hold, but the conceptual structure supporting them seems to rest on foundations we can't quite examine without exposing unresolved tensions. This creates a peculiar kind of stability, practical but philosophically fragile. Consider what happened with turbulence. The Navier-Stokes equations were written down in the 19th century. They describe fluid flow with remarkable precision. Engineers use them to design aircraft, predict weather patterns, model blood flow through arteries. The equations work, but we still don't understand turbulence, the chaotic, swirling complexity that emerges from those same equations under certain conditions. Turbulence has been called the last unsolved problem of classical physics. That label undersells the strangeness. We have the equations. We know they contain all the relevant physics, but extracting a theoretical understanding from them remains an open challenge. The equations form what's essentially a gigantically complicated, non-linear oscillator, sometimes stable, sometimes wildly unstable, often exhibiting what looks like spatio-temporal chaos. Physicists can simulate turbulent flows on computers with increasing accuracy. They can identify patterns and scaling laws empirically. But they lack a fundamental theory explaining why turbulence behaves as it does, what determines its characteristic structures, how energy cascades across scales. The mathematical description is complete. The conceptual grasp remains absent. This mirrors what we've seen elsewhere: complete equations that resist complete understanding. The Clay Mathematics Institute recognized this by making the Navier-Stokes existence and smoothness problem one of its 7 Millennium Prize challenges. The question isn't whether the equations describe reality. They demonstrably do. The question is whether smooth solutions always exist, or whether the mathematics itself can fail to remain well-defined, producing infinities that signal theory limits. Even more unsettling are problems that can be proven unsolvable. In quantum mechanics, the spectral gap problem asks whether there's an energy gap between a system's ground state and its first excited state. This matters enormously for understanding phase transitions, superconductivity, magnetism, fundamental behaviors of matter. But it's been proven that no general method exists to determine whether a given quantum system has a spectral gap. This isn't like saying we haven't found the solution yet. It's saying no solution can exist, even in principle. The problem is mathematically equivalent to questions Alan Turing proved undecidable. Certain aspects of quantum systems are fundamentally beyond algorithmic determination. Even perfect knowledge of microscopic properties won't necessarily let you predict macroscopic behavior. The derivation from small to large, from quantum to classical, contains formal barriers. The pattern keeps recurring. Physics provides tools that work, equations that predict, methods that calculate, frameworks that organize. But when you push toward complete theoretical closure, toward answering why these tools work or what they mean, you encounter the same barriers. Infinities requiring renormalization, interpretations that can't be distinguished empirically, problems proven undecidable, predictions that conflict with direct experience. The three-body problem offers perhaps the clearest historical example. Newton could solve the motion of two masses attracting gravitationally. A complete, closed-form solution exists. Add a third mass and everything changes. No general solution exists. The system becomes chaotic for most initial conditions. Despite centuries of effort by exceptional mathematicians, we know only 5 families of periodic orbits. The rest of possibility space remains analytically inaccessible. This matters because it demonstrates something fundamental. Even deterministic systems, governed by well-understood laws, can exhibit behavior we cannot predict analytically. Mathematics alone doesn't always suffice. The equations exist, the motion is determined, but extracting complete understanding from those equations proves impossible. Physicists have learned to live with this. They use numerical methods, approximations, statistical approaches. They make progress without closure. The pragmatic success is undeniable, but it comes at the cost of accepting that certain aspects of even simple systems will always require computational rather than analytical treatment. That understanding comes in degrees rather than as an all-or-nothing proposition. Renormalization reveals the same pattern from a different angle. When calculating quantum field properties, infinities appear that would make the theory meaningless. Renormalization involves absorbing these infinities into measurable parameters, effectively redefining the problem to eliminate the infinities. It works extraordinarily well. Quantum electrodynamics makes predictions accurate to 10 decimal places. But even its pioneers found the procedure unsettling. Feynman called it a dippy process, admitting that having to resort to such techniques prevented proving the theory mathematically consistent. Dirac, who helped develop renormalization, later wrote that it was just not sensible mathematics. The criticism centered on subtracting one infinity from another to get finite results, a procedure at odds with conventional mathematical rigor. The physical interpretation remains debated. Perhaps the electron has an unbounded bare charge in the formalism, but quantum field effects screen this infinity, leaving only the modest charge we measure. Perhaps the infinities signal that our theories break down at short distances and need replacement by something more fundamental. Perhaps renormalization is revealing something true about how scale works in nature, that different energy regimes are effectively disconnected, allowing us to ignore high-energy details when calculating low-energy phenomena. What's certain is that the technique works while its justification remains philosophically uncomfortable. We have a calculational procedure that produces correct predictions but requires mathematical moves that violate the rules we normally follow. The success is empirical rather than deductive. We cannot prove the theory consistent in the way we'd prefer. We simply observe that it keeps working. This pragmatic acceptance characterizes much of modern physics. When theoretical closure proves impossible, physicists develop workarounds. Effective theories valid within certain regimes, calculational techniques that bypass foundational issues, interpretational frameworks that partition the problem space into manageable pieces. The field continues making discoveries, refining predictions, expanding domains of application. But the underlying conceptual tensions remain unresolved. The question becomes whether resolution is even possible. Perhaps physics has reached a point where further progress requires accepting that complete mathematical description won't always translate into complete conceptual understanding. Perhaps certain questions that seem physical are actually undecidable. Perhaps our theories will permanently contain elements that work pragmatically without being fully justified foundationally. This would represent a profound shift in how physics relates to knowledge. The expectation since Newton has been that understanding nature means finding mathematical laws that both predict phenomena and explain why those phenomena occur. Prediction and explanation were assumed to converge in sufficiently developed theories, but what we're seeing suggests they might diverge, that we can have tools that work without fully understanding why they work or what they mean. The recurring impossibilities aren't random obstacles. They share structural similarities, breakdowns at extreme conditions, mathematical infinities signaling theory limits, interpretational ambiguities that can't be resolved empirically, problems proven undecidable, gaps between what we can calculate and what we can conceptualize. These similarities suggest something systematic about where physics encounters its boundaries. Gödel's incompleteness theorems showed that mathematical systems contain true statements that can't be proven within those systems. Perhaps physical theories face analogous limitations, that complete self-contained understanding is impossible even for theories that are empirically adequate. The tools we use to describe nature might be inherently incapable of fully explaining themselves. This doesn't make physics arbitrary or unreliable. The empirical success remains real and impressive, but it suggests that success operates within boundaries we're only beginning to recognize. We've built a magnificent structure of knowledge while standing on foundations we can't quite examine without risking the structure's stability. The practical utility is undeniable. The philosophical security remains elusive. What makes this particularly striking is how the same problems keep reappearing. Renormalization in quantum field theory, interpretational ambiguity in quantum mechanics, singularities in general relativity, undecidability in quantum materials, chaos in classical dynamics, turbulence in fluid mechanics, different domains, same conceptual barriers. Physics hasn't been slowly clearing these obstacles. It's been repeatedly encountering them in new contexts while developing increasingly sophisticated ways to work around them. Perhaps the most unsettling aspect isn't that physics hasn't solved these problems. It's that the problems persist unchanged, no matter how much precision we gain or how many phenomena we explain. The recurring impossibility isn't a temporary gap in knowledge. It appears to be a permanent feature of how our most successful theories relate to reality. We can predict without fully understanding. We can calculate without complete conceptual clarity. We can make progress while leaving fundamental questions unresolved. And perhaps that's not a problem to be solved, but a condition to be recognized. The real question isn't whether physics will eventually solve these problems. Maybe it will. Maybe quantum gravity will arrive, elegant and complete, resolving singularities and unifying forces. Maybe we'll discover that renormalization reflects something profound about scale and structure rather than mathematical sleight of hand. Maybe turbulence will yield to new mathematical frameworks we haven't invented yet. But there's another possibility worth considering. What if these recurring impossibilities aren't temporary obstacles, but permanent features of how mathematical description relates to physical reality? What if the universe simply doesn't permit the kind of exhaustive theoretical closure we've been seeking since Newton? This isn't defeatism, it's recognition. Physics has achieved extraordinary things by learning to work within these constraints rather than waiting for them to disappear. We simulate what we can't solve analytically. We apply renormalization despite its questionable foundations. We use quantum mechanics without consensus on interpretation. We study black holes while acknowledging singularities as theory breakdowns rather than physical objects. This pragmatic approach has been remarkably productive. It's given us GPS satellites that account for relativistic time dilation, quantum computers exploiting superposition and entanglement, materials engineered at the atomic level, the Large Hadron Collider discovering the Higgs boson exactly where calculations predicted. None of this required resolving the foundational puzzles. We learned to build on uncertain ground. What's gradually becoming clear is that this might not be a temporary compromise. The pattern is too consistent, appearing across too many independent domains. Classical mechanics encounters chaos. Fluid dynamics produces turbulence. Quantum mechanics admits incompatible interpretations. Field theory requires renormalization. Gravity predicts singularities. Materials exhibit undecidable properties. Different theories, same conceptual barrier. This suggests something structural rather than accidental. Perhaps mathematical description and physical reality don't map onto each other as perfectly as we assumed. Perhaps our equations are interfaces, tools calibrated for prediction within specific domains, rather than transparent windows onto underlying truth. They work extraordinarily well for their intended purpose, but that purpose might be more limited than we thought. Consider what this means for the grand project of theoretical physics. For centuries, the implicit goal has been finding the final theory, the complete mathematical description from which everything else follows. String theory and loop quantum gravity represent the most sustained attempt at this. Both frameworks are mathematically sophisticated. Both attempt to resolve the incompatibility between quantum mechanics and general relativity. Neither has produced a uniquely testable experimental prediction, distinguishing it from alternatives. This stalled progress might not reflect insufficient cleverness. It might indicate we're pushing against a genuine boundary. If Freeman Dyson was right that quantum and classical descriptions could peacefully coexist without unification, then the search for a theory of everything pursues something that doesn't exist. Not because we haven't looked hard enough, but because reality may not be structured that way. The evidence accumulates quietly. Undecidable problems in quantum systems, chaos in deterministic equations, infinities requiring absorption through mathematically unconventional procedures, interpretational ambiguities that persist despite empirical success, singularities marking theory limits. Each instance alone might be dismissed as a specific technical challenge. Together, they form a pattern suggesting systematic limits on what mathematical physics can reliably achieve. What makes this particularly difficult to accept is how it conflicts with the narrative of scientific progress we've internalized. That narrative says each generation solves the previous generation's mysteries, revealing deeper laws beneath apparent complexity. Newton unified terrestrial and celestial mechanics. Maxwell unified electricity and magnetism. Einstein unified space and time. The pattern encouraged belief that continued unification would eventually produce complete understanding. But the recurring impossibilities suggest a different pattern. Each unification reveals new mysteries. Each deeper theory encounters new barriers. The complexity doesn't disappear, it migrates to different levels. We solve specific problems while the general problem of extracting complete understanding from mathematical description persists unchanged. This doesn't invalidate what physics has accomplished. The predictions remain accurate. The technology works. The experimental confirmations are real. But it reframes what these accomplishments mean. They demonstrate that we can build extraordinarily powerful tools for navigating reality without necessarily understanding what reality fundamentally is in itself. Prediction and explanation, assumed to converge, might actually diverge as theories become more sophisticated. The three-body problem showed this centuries ago, though we perhaps didn't fully register the implication. Adding a single additional mass transforms a solvable system into one exhibiting chaos, deterministic but unpredictable, governed by known laws yet resistant to analytical solution. This wasn't a failure of mathematics or physics. It was a revelation about deterministic systems. They don't always permit the kind of prediction we expect from complete knowledge of initial conditions and governing laws. Turbulence reinforced this lesson at a different scale. The equations exist, they accurately describe fluid behaviour. But extracting theoretical understanding of turbulence from those equations remains an unresolved challenge despite 2 centuries of effort. The mathematics contains something we cannot access through analytical methods. Simulation works. Approximation works. Complete theoretical derivation doesn't. Renormalization added another layer. Here we have a technique that produces spectacularly accurate predictions through procedures its developers considered mathematically questionable. The theory works while its logical foundations remain conceptually unsettled. This suggests that empirical success doesn't guarantee theoretical coherence, that we can have tools giving correct answers without fully understanding why those tools work or whether they're logically justified. The quantum measurement problem makes this explicit. The theory splits into two incompatible descriptions: smooth Schrödinger evolution and sudden measurement collapse. These cannot both be fundamental within a single unified account, yet the theory works regardless of which interpretation you adopt. Many worlds, pilot waves, spontaneous collapse, they all reproduce the same predictions. The mathematics succeeds while the physical meaning remains ambiguous. Singularities mark where theories explicitly announce their own breakdown. General relativity predicts infinite curvature. Quantum field theory generates infinite corrections. These infinities don't represent physical quantities. They're signals that the theory has exceeded its recognized valid domain. But rather than treating this as crisis, physics developed methods for working around these breakdowns: approximations near singularities, renormalization for infinities. The spectral gap problem proves that some well-posed questions have no algorithmic solution. Even perfect microscopic knowledge won't always yield macroscopic predictions. The derivation from fundamental to emergent contains insurmountable barriers. This isn't about computational limits or missing information. It's about logical structure. Some questions are undecidable in a formal mathematical sense. What emerges from this accumulation is a picture quite different from the one physics textbooks typically present. We don't have theories that completely describe reality in domains where they apply. We have theories that make accurate predictions in those domains while containing conceptual elements we cannot fully resolve. Interpretational ambiguities, mathematical procedures lacking rigorous justification, questions proven unanswerable, problems resistant to analytical solution. This doesn't make physics arbitrary or unreliable. The empirical grounding remains solid. The predictive power is real. The technological applications work. But it suggests that what we're doing is more subtle than straightforward description of reality's fundamental structure. We're developing increasingly sophisticated tools for navigating and predicting within specific domains, while the question of what those tools represent remains open. Perhaps this is what mature science looks like. Not a progression toward complete knowledge, but an expansion of predictive capability accompanied by deepening awareness of where prediction breaks down. Not the accumulation of eternal truths, but the refinement of effective theories useful within recognized limits. Not the discovery of reality's fundamental nature, but the construction of increasingly powerful interfaces for interacting with reality. This perspective doesn't diminish physics, it changes what counts as success. If complete theoretical closure is impossible, if the relationship between mathematics and physical reality contains irreducible gaps, then continuing to make progress despite these gaps represents genuine achievement. We learn to calculate without complete understanding. We develop tools that work without full justification. We made predictions despite interpretational ambiguity. The recurring impossibility isn't a problem physics has failed to solve. It's a feature of how physics operates, how mathematical description relates to physical phenomena, how prediction diverges from explanation, how theories succeed practically while remaining philosophically incomplete. Recognizing this pattern doesn't mean abandoning the search for deeper understanding. It means adjusting expectations about what understanding means and what physics can ultimately achieve. What's most striking is how physics continues advancing despite these persistent barriers. New phenomena are discovered, more precise predictions emerge, technology becomes more sophisticated. The recurring problems don't prevent progress. They constrain it in specific ways while leaving enormous room for continued development. We work around the impossibilities rather than waiting for them to resolve. This pragmatic success might be the most important insight. Physics doesn't require complete theoretical closure to be useful, accurate, or progressive. It requires predictive frameworks that work within recognized domains, experimental methods that test those predictions, and the intellectual honesty to acknowledge where our tools reach their limits. The recurring impossibility marks those limits without determining how much we can accomplish within them. And perhaps the most unsettling part isn't that physics keeps encountering the same impossible problem. It's that this encounter has become so normalized, we rarely question whether the problem might be inherently insoluble. Not because we lack sufficient ingenuity, but because reality itself doesn't conform to the kind of complete mathematical description we've been seeking. The impossibility recurs not as obstacle but as signal, pointing towards something fundamental about how knowledge and nature relate. We've learnt to read the equations, we haven't learned what they're trying to tell us about their own limitations.